So we've got this idea that in certain cases, it might make sense to integrate a function across the whole real number line. Now, the applications for this will come up differently depending on different majors. So I just want to focus on the way we would handle that. Now, the notation looks like an ordinary integral. So I have the integral of f of x dx. My lower bound is going to be some real number a, but my upper bound is infinity. So this is one way to notate an improper integral. Again, it's called improper because we cannot just use fundamental theorem of calculus on this. The way that we actually calculate this kind of integral is that we're going to take a limit. So this integral is going to be the value of the limit. Here I'm taking a limit as the variable t goes to infinity. I'm still integrating f of x dx, but now I'm integrating from a up to t. And as long as this limit of the integral exists, that will be the value of the improper integral. Let's work on integrating 1 divided by x squared dx between 1 and infinity. This was exactly the problem where it looked like we had a limit. So the first thing I'm going to do is I read my notation. It says integrate from 1 to infinity. The integrand is 1 divided by x squared dx. So the limit I need to set up will be the integral from 1 up to t, as t goes to infinity. And I am still integrating 1 divided by x squared dx. So the integrand stays the same. The lower bound stays the same. The upper bound is now a new variable. And that variable is going to go to infinity. Now, I'm just using the x and the t here as a matter of convention. If your integral already had t variables in it, you will need to use something different for the limit operator. But since this is the very first lecture where I'm talking about this stuff, I will use the conventional notation. Now, when I'm faced with a limit like this, it's important to remember that this integral by itself is defining a function. So different values of t will give different values of the integral, right? This formula is a function of the variable t. Even though it's set up to look like an integral, which it is an integral, integrals tell us area. Change the t value. You're taking a wider interval, a wider base for that region, so you'll get a different value for the area. When I actually go to compute this, what I'm going to do is use the fundamental theorem of calculus inside of the integral. So I'm going to say I'm taking the limit of this integral. The integral is the integral of 1 divided by x squared. And I'm actually going to rewrite that first as the integral of x to the power minus 2. And I only do that so I have an easier time using fundamental theorem of calculus. I can use the power rule. Now, when I use the fundamental theorem of calculus, inside of the limit, I have a definite integral. So I'm going to find an antiderivative. My antiderivative is going to be negative x to the power minus 1. Fundamental theorem of calculus says I need to evaluate that function at x equals t, and I need to evaluate that function at x equals 1. And the difference of those two evaluations is the amount of area represented by this integral. So I've done that here, and I've actually left out one of the middle steps. So this simplifies to 1 minus 1 divided by t. That is the value of this integral. And once again, a different value of t here gets me a different amount of area. So this integral here inside of the limit is a function of t. It's just a different way to write the function 1 minus 1 divided by t. And written out like that, it should not be surprising to say that as t tends to infinity, this function, 1 minus 1 divided by t, is tending towards 1, just like we saw on the graph. So the improper integral from 1 to infinity of 1 on x squared dx is equal to 1. We've assigned that area the value of 1, even though it stretches off across the whole real number line. It has 1 unit of area covered underneath there. Let's see what happens when we try to integrate the other function. The other function I had was y equals 1 divided by x. So I'm going to use the very same technique. I'm going to set up a limit to calculate this integral. So I've introduced an extra variable t. I'm going to integrate the function 1 divided by x dx between 1 and t. T is some variable, but I can use the fundamental theorem of calculus inside the limit. This whole expression is defining a function of t, and I want to calculate the limit of that function as t goes to infinity. So the steps are, on the face of it, similar, but I use a different antiderivative. The antiderivative for 1 divided by x is, of course, the natural log function. So the fundamental theorem of calculus says that inside of the limit here, I have the natural log of x. I evaluate at x equals t, and I subtract at the point x equals 1. So I'm taking the limit as t goes to infinity of the natural log function minus 1. But the natural log function increases forever. Natural log function grows without bound. It does that very slowly, but it does eventually surpass any bound I can put on it. There's a point at which the natural log will be larger than 2. There's a point at which the natural log will be larger than 2 million, and it'll keep going. So this limit does not exist, right? You could say that it's going to infinity, but that's not a real number, so I'm not going to assign that as the value of my integral here. So this is an example where I'd say that the improper integral diverges. It's the same language we would use for the limits themselves, right? Limits can converge. We'll get a real number as the answer. Limits can diverge, and that's when we don't get a real number. Improper integrals are just a way of dealing with integrating across an infinite range, which requires us to use limits. Some of the time we can say that that improper integral will converge to a number, and that'll be the amount of area that we've highlighted underneath the graph of our function. In other cases, the integral will diverge and we don't get an amount of area. Let's take a look at a more complicated situation here in a bit.